Welcome back to Labs in the Time of Coronavirus. Today's video is a partial walkthrough of one of the labs that is done partially in class and partially at home. This is a lab that normally we would do somewhere around the middle of the semester after you have been at least partially familiarized with the idea of vectors and especially with force as a vector. So let's close this thing down. This is the lab that is addition and resolution of vectors. Normally it would be the 7th or so lab out of 10. This semester it's the second in-class lab, or one of the two that we're doing on the second in-class day. It is actually a fairly quick lab in class. I'm not going to necessarily walk you through everything on this lab. You are supposed to be doing this on your own. I did, however, want to walk you through a little bit of how to do this stuff, basically breaking a vector into components, and a brief walkthrough on how to add vectors, and also a little bit about the notation used in this handout. Because you really need to do as much of this lab at home before showing up to lab on your assigned lab day, rather than showing up with this blank piece of paper, sitting down and starting to do all this stuff. Because if you do the latter, then you won't have time to get the data, which shows up actually in these 3 columns. Literally everything up until these 3 columns is something that you can do at home without any equipment. You just need your pen or pencil, some graph paper, and a calculator, and a ruler, and a protractor. Okay, so hopefully this video will help you to do all of the calculations before showing up to class, so that when you're in class you just take the data. Alright, so there's a little bit of stuff in the pre-lab questions about adding vectors and using vector components in I-hat, J-hat notation. I-hat, J-hat notation basically just means that you are using the vector with a component along the x direction and a component along the y direction. So if I open up my workspace here, basically we need to make a scale in here somewhere. So I might make a scale that says that each one of these boxes, this length right here, is 1 in the I-hat, and this length right here is 1 in the J-hat direction. So I-hat, J-hat direction can be the same. The other thing that I have to do is pick a location to be my origin. So for example, this location could be my origin for my system. Now suppose that I have a vector that is, let's say 2 I-hat and 3 J-hat. So vector 1 can be 2 I-hat plus 3 J-hat. So I need to go 1, 2 I-hats, 1, 2, 3 J-hats. The vector should end here. It should start at the origin. And then to draw that vector, you'd ideally use a ruler. I don't have one, but I have the next best thing, which in this software is that I can select the line tool. So my vector begins at the origin and it ends here at this point. If I have another vector that I need to add to it, so let's say vector v2 is, let's make it 3 I-hat plus 5 J-hat. So 1, 2, 3, 1, 2, 3, 4, 5. Okay, so my new vector would start here and it would end here. And you'll we'll see that these two vectors are very nearly overlaid with each other. They're not quite exactly, but pretty close. So there's that one. And if I wanted to add the two vectors together to get a resultant vector, so let's say that I decide that I want to add some vector. We'll say that the vector is maybe like r, and it can be v1 plus v2. The way that I do that is I add the components. You could think of the I hats and the j hats as being like x's and y's. So I have 2 I hat plus 3 j hat, to which I am then adding 3 I hat plus 5 j hat. And so what I end up with, 2 plus 3, that's 5 in the I hat direction, and then 3 plus 5 gives me 8 in the j hat direction. All right, so my resultant vector, I could look at it as here is my first vector, and I'm doing a tip to tail. Okay, so I could draw it by now taking one that goes over 1, 2, 3, and then up 1, 2, 3, 4, 5. So it needs to end somewhere over here from this location. So to do that, I draw my vector like this, and that is the addition of these two vectors. All right, so let's do another example. This other example, let's get some fresh graph paper in here. So same scale as before. This time maybe we'll have two vectors. We'll say vector number, or vector A could be, say, 5 I hat plus 7 j hat, and maybe vector B is 4 I hat minus 2 j hat. Okay, so again, we'll put our origin down here. If I'm going to draw the two vectors individually, zoom out a little bit there. Vector A would maybe begin here, and we'd go over 5, so 1, 2, 3, 4, 5. We have to go up 7, 1, 2, 3, 4, 5, 6, 7. So vector A would be like this, starting here at the origin, ending right here. Okay, and then vector B says go over 4, 1, 2, 3, 4, go up -2, so that's the same as go down 2, 1, 2. So here's vector B, and now I can draw that out with this line right here. Okay, so I've drawn vector A, I've drawn vector B. Then what I'm going to do is maybe I want to add the two of them. So to add them, here's vector A, B, 1, 2, 3, 4, and down 2, 1, 2, would end me right here. You'll notice, that these two vectors that I've drawn to represent B are parallel to each other. So this line and this line are parallel to each other. That's not any coincidence. Vector B, if you move around the vector, A or B or any vector, just moving it creates another vector that is parallel to the first one. The I hat, j hat part will still be the same. It's just you have a different start location, so you have a different end location, but they will be otherwise parallel. What's the resultant vector? So this is vector A. This is vector B. This also is vector B, or if you want, you could call it vector B prime since it's been shifted from the origin. Okay, and then vector A plus B should start at the location where vector A started from. That's right here. And it should end at the location where vector B prime is ending at. Okay, so that takes us to right there. So this last one that I've drawn, this one right here, would be vector A plus B. If I wanted to do vector A minus B, so up here again, this is A, this is B, minus B just means put a minus sign in front of everything here. So we have minus 4I hat plus 2J hat. Okay, so minus B, we go 1, 2, 3, 4, 1, 2. So this would be the minus direction for B. Okay, so we draw our line here. You'll notice that B and minus B are essentially along a single line. They just point in exact opposite directions. So minus B. All right, and so our last vector would be vector A minus vector B. So we begin at the origin and we end right here. Okay, and so that is the vector for A minus B. All right, so A minus B. Okay, so that actually is the basics of how to add them with drawings. The other thing you can do is just add them algebraically. A plus B should be 5I hat plus 7J hat, and then to that we're adding 4I hat minus 2J hat. So 5 plus 4 gives me 9. That's in the I hat. 7 minus 2 is 5J hat. So if we come down here, and count a little bit, what we find is we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is in fact 9, and then 1, 2, 3, 4, 5. Okay, so these vectors have added up graphically the same way that they've added up algebraically. Okay. To this we have to add one more layer. That one more layer is that very often vectors are not specified in I hat and j hat terms. They might be specified in terms of a magnitude and a direction. So for example, maybe we have a vector that is, say, let's call this vector C. And vector C can be, I don't know, we could call it like 10, 90 degrees, for example. So oftentimes we'll write it with curly brackets like this. So 10, 90. In general, the left-right direction, starting from the positive x-axis, that's 0 degrees, and then you go counterclockwise to measure your angle. So 10, 90 means go 10 units in the y direction. So that would end up right here. That's your vector C. And in principle, these two could be any numbers you want. If that's the case, then probably when you're going out to draw them, you're going to want a ruler. And the ruler is so that you can make a scale. So make a scale. For example, you might say 1 centimeter on the ruler is equivalent to, well, in today's lab, we're doing stuff in units of kilogram or gram.g. So maybe we'd say 1 centimeter is equivalent to, say, 10 grams dot g, okay, etc. And then you need a protractor. The protractor is so that you can actually measure the direction in which these lines are being drawn in, or these vectors are being drawn in. So this gets you direction. Okay. So basically, again, there are two ways to add your vectors together. One of them is to do tip to tail like I was doing here. But now imagine that your tip to tail, you have to use a ruler and protractor to draw the first one, and then you use a ruler and protractor to draw the second one after it. So it's like you're given a direction. Oops, that's not what I meant to do. You're given a vector and you're told the first vector is in some particular direction, it has some particular magnitude, so you draw it. Then you start the next one from there, and you make a sort of, I guess like you call it a miniature origin at the location of the end of the other vector. So you have your x-axis, you have your y-axis again. And now you're going to start your next vector here, and your next vector goes off in some particular direction, has some particular magnitude. And you can do this multiple times. You know, you may be adding 3 or 4 vectors together. Okay, so make a new origin here where this is located. Maybe the next one says so much distance in the 225 degree direction or whatever. So now you end up with one that's over here, and so on. And you just keep drawing these until you get to the last one, and then your resultant vector starts at the start of the first vector and ends at the end of the last vector. So there's the resultant vector for this addition. And so at this point, you basically get out your ruler and you'd measure the length of this, and that converts you to a magnitude, and you'd measure the direction of it, and that gets you an angle theta. Okay, so that is the graphical method for adding vectors together. And I'm just drawing the little heads on them so that you can see what direction we went in. So this is like vector 1, vector 2, vector 3, and then the red one is the resultant. Resultant is v1 plus v2 plus v3. Okay, so that is the geometric method for adding vectors. There's a second method for adding vectors in general. This is more of the algebraic method. And the way that it works is that you basically start with your vector in polar form again. So maybe your vector is given by, let's say, 15 gram.g, comma, 45 degrees. And then maybe your next vector, v2, can be given by 25 gram.g, comma, maybe this one is in the 120 degree direction, for example. Okay, so step 1, get in Cartesian form. Okay, Cartesian form means x comma y, or basically v1x I hat plus v1x j hat and v2x I hat plus v2x j hat. Okay, so to do that, basically what you do is you imagine, and you can just kind of sketch this, if you will. You can imagine that vector v1 is given right here, and then you have an x-axis and a y-axis. So let's go ahead and just draw a nice x and y-axis in here. So here's your y-axis, here's your x-axis. You can imagine that the x-axis, I should maybe have drawn it a little longer. Your x-axis comes out here, more or less horizontal. Your y-axis comes way up here, more or less vertical. And you basically end up with projections onto both axes of this line. So imagine drawing a line straight down from the top of this, or straight up if it happens to go into one of the lower quadrants. And wherever it hits this axis, that is basically determines where the projection is going to be. And so you basically end up with a triangle that looks like this, where this right here, this right here is angle theta, and theta is this number here, the direction. Okay, and V1, without an arrow over it, would be the magnitude. So this is 15 gram dot g. This is 45 degrees. Okay, so now what we're trying to do is solve for V1x and V1y. Alright, so you have the hypotenuse and you have an angle, so you can use your trig identities. So you use sine of theta is opposite, that'd be V1y over hypotenuse, so over V1. Cosine of theta is V1x over V1. Okay, so solve for V1x and V1y. This one now says that V1y is V1 sine theta 1. This one says that V1x is V1 cosine theta 1. Okay, so V1x and V1y. V1x is 15 gram g times cosine of 45 degrees. So at this point you have a calculator problem. So when you put this into the calculator, make sure that you are in degree mode since you're working with angles in degrees. If you do that, then let's see, got to turn mine on, got to put it in to degree mode. Yep. So 15 gram g times cosine of 45 gives us 10.606. So maybe we would say something like probably 10.6 is sufficient. And this one you'd have 15 gram dot g times sine of 45 degrees. At 45 degrees, sine and cosine give you the same answer, so you get 10.6 again. Okay. So now you got to repeat it for the other one, for V2. So, to do that, maybe what we do is move this guy up a little bit. We're looking at 25 and sine and cosine of 120. So you can draw the diagram again if you'd like, but you can just plug the numbers in now that we've seen this. So V2x is 25 grg times cosine of 120 degrees, and V2y should be 25 grg times sine of 120 degrees. So when you plug in the cosine of 120, you should get a negative number. When you plug in the sine of 120, you should actually get a positive number. They won't be the same magnitude at this point. So cosine of 120 should give us a half. So you end up with, or negative a half, so you should end up with negative 12.5 for this one. And then for this one, 25 times sine of 120 gives us 21.65. So we'll call that 21.7 gr.g. Okay. Now, we've done this. Now we're ready for step 2, which is add them together. And step 2, add them together, is basically the same thing that we did before on just the graph paper. So V1 plus V2 would be V1 x I hat plus V1 y j hat, and to that we're adding V2 x I hat plus V2 y j hat. This is a V2x. This is V1. All right. So basically you have 10.6 minus 12.5 in the I hat direction. So we plug in 10.6 minus 12.5, we get negative 1.9. So minus 1.9, and that's in the I hat direction. And then for the j hat direction, you have 10.6 plus 21.7. So 10.6, 21.7. This ends us with 32.3 j hat. Okay, so that's step 2. Step 2 is just straight algebra. Step 3 basically is that you want to convert everything back to polar form. So now that I've moved this guy up here, we can write here step 3. Convert to polar. Okay, and so step 3, the way that convert to polar works is we basically can come here and put our graph paper back in for what it's worth. Basically, if this is our origin point right here, we're going minus 1.9, so maybe like to here. We're going plus 32, which takes us off the page. So maybe our y direction, we make up a different scale so that this represents 1, 2, 3, or 10, 20, 30. So 32 would basically be about right here. So we're looking at a point that's roughly right here. Okay, and so you could draw it. Starts off here, ends up basically there. Okay, and now you'd have to measure the length of this line, and you'd have to measure the angle. What's the angle that you're measuring, you may wonder? Oops, it's not what I wanted. Although you probably could use this guy to do it. There's also a ruler for what it's worth. So our ruler would begin here, would end here. Okay, and actually at the bottom it's showing us an x comma y and an angle. I guess this ruler is not especially useful, but in principle you'd use a regular ruler and you'd measure the length of this guy, and then you'd take a protractor and you'd measure the angle. Now this actually isn't going to work because I've changed one direction relative to the other. In other words, I had to treat each one of these as if they were 10 instead of as if they were 5 to fit it. Let's see. 1, 2, 3, 4, 5, 6. I guess we could start it over here. So we could try it again. Our delta x would be here. Our delta y would take us up to about here. So we're looking at something that's maybe about here if we're drawing it really to scale. If you're going to draw it, you might as well draw it to scale. Start here. Go here. Okay. So with your protractor, you would actually be measuring this angle right here from positive x-axis to wherever your line is. With your ruler, you'd be measuring the length from this location to this location. Okay? So that's one way of doing it. The other way, since the idea was to do this algebraically, we can convert it to polar by just making a simple sketch here that's not to scale. So here's my y-axis, my x-axis. I know that it's going to be somewhere in this quadrant. So I'm just going to draw a line that's basically in this quadrant somewhere. All right. Now you turn it into essentially a triangle. And one way you can do that is by basically just saying, all right, here's y, here's x. X and y always make a right angle together. This angle right here we're going to call phi instead of theta. Okay, and this right here would represent my v, my sum. We'll call this again r. So this side right here would be v1 plus v2, which is in the x part, the rx, the prescription, if you will. And this would be ry. Okay, so tangent of phi is always the opposite from phi, so that's rx, divided by the adjacent to phi, that's ry. And then r is always given by Pythagorean theorem, rx squared plus ry squared. And notice that phi and theta are related. Basically, theta is 90 degrees plus phi for this particular triangle. So plugging in numbers, this one right here, rx over ry, we'd have 1.9 divided by 32.3. Notice that I'm getting rid of the signs here because I'm already keeping track of which direction it is by what quadrants it's in and what I had to add to phi in order to get theta. Okay, so if I take the inverse tangent, that's the tan negative 1 button of 1.9 divided by 32.3, I end up getting 3.366, so about 3.4. So this is roughly 3.4 degrees. That means that this is 93.4 degrees. Okay, and then this one right here, this is 1.9 squared plus 32.3 squared. Again, the sign here isn't going to matter because you're squaring, so everything is positive anyway. 1.9 squared plus 32.3 squared gives me 1046. Okay, so r squared is 1046.9 actually. That means that r, we take a square root, and that's 32.3558. So we could call this, say, 32 32.4. Okay, so adding the two together gives me 32.4, and I guess these were in gr.g's, so gr.g, comma, 93.4 degrees. All right, so we've basically done the addition of two vectors. There's actually a step 4 involved here that goes with the experimental side. So this actually gives you the answer that you're looking for. So you basically say, yep, here's the answer. To get the experiment right, you're making use of a thing called Newton's first law. And so the vectors in question that you're adding here are actually force vectors. And the basic setup, the experimental setup that you're using, is that you have essentially a ring like this, and then there's a little spindle that the ring is sort of placed around, and then you have a string, you have a string, and you have a string. And so this might be like force F1, this might be force F2. If you add the two of them together, you're going to end up with some force maybe off in this direction, for example. F1 plus F2 would be like this. Experimentally, how you can find this is that you're trying to balance the ring. And Newton's first law says that if you add all the forces on an object and they add to 0, then the object is not accelerating. You're balanced. So this right here has to be the negative of F1 plus F2 in order for this ring to be balanced. In other words, in order for it to just sit there without touching the spindle on any side. Okay, so to find the negative of a resultant vector, what you do is you take the direction and you either add or subtract 180 degrees. So negative r, in this case, would be 32.4 gr.g, and then 93.4 plus 180 gives you 273.4 degrees. So this is basically telling you that if you put a force of 32.4 gr.g in the 273.4 degree direction on this guy, then it will be balanced, assuming that you've got force F1 and F2 represented by basically V1 and V2. Okay, so the last thing that you need to know in order to do this lab at home is, and you don't really need to know this, but it's maybe just like useful information when you get to lab in particular. What does gr.g mean? So gr.g is a unit of force, and what it's equivalent to is 1 gram of mass suspended in Earth's gravity field, G. Okay, so in the lab, if you see something that says the force needs to be, say, 100 gr.g, what that basically means is you need to have 100 grams suspended from the end of the string that's applying this force. Okay, so 100 gr.g implies suspend 100 grams from the string. Okay, that counts the mass hanger. So whatever weight hanger, whatever mass hanger you're using, that plus any mass is added to it totals 100 grams. All right. So I think at this point I've basically given you the calculations walkthrough of this experiment, what you'll need to do is basically answer these pre-lab questions. So you're basically doing similar to what I started off doing, which is adding some simple vectors, drawing them here in this form, etc. Then your next thing is that you are given a set of forces that you're going to be basically adding together to find the resultant. And so the first step to do it algebraically is to break each one of these into an x component and a y component. So 200.2 newtons, for what it's worth, is the same thing as 0.2 kilogram meters per second. So it's roughly 20 grams dot g. Okay, and depending on what our lab setup person puts out this week on the lab tables, we may actually have to modify what forces you're adding here, but I'll only modify it by multiplying everything by a factor of 10, essentially. So if she puts the big weights out, then we may have to change this from 0.2 to 2 newtons. And then this one is 2 newtons and 2 newtons and so on. Okay. So basically that's all you're doing. Once you have them in x and y form, in Cartesian form, you can add vectors using the analytic method. And you have to ultimately convert them back into polar form. So you have a magnitude and a direction for each of these. Okay. Without converting them, leaving them in polar form, you can solve graphically. That's where you draw tip to tail. And then you measure the resultant vector using a protractor and a ruler. You should end up with the same answer here as you got here. You should end up with the same answer here as you got here. You should end up with the same answer here as you got here. Okay? All of that you should be able to do before you show up to lab on Tuesday or whatever your lab day is. Okay, so you need to be doing this as soon as you have the chance, but before lab starts. The experimental method is that you're going to literally come to lab, you're going to hang actual weights from the strings, and then you're going to find how much weight you can hang from the third, or in the last case, fourth string, and still have the system balanced. And then and where you have to put that string to make it balance. And then where you put it gives you the direction, how much you hung from it gave you the magnitude, and since you are balancing it, you have an extra minus sign, so you just take your direction and either add 180 or subtract 180 from it, so that you have an answer that's between 0 and 360 degrees, and that is the actual resultant vector. That's what you're actually doing in lab. So if you've done your job by doing all of this before you show up to class, to your lab, then you should be able to show up to lab. There may be a brief explanation to counter for the fact that the amount of weights on this handout may end up not matching the amount that get put out on the tables. So we may have a brief calculation for that. But once that's done, you should be able to very quickly set up your system, show that it's balanced, write down what it is that you need to balance it, and therefore finish the lab. It should take you maybe 15 minutes, if that, if you've done everything correctly. Okay, so that's about it from me. I may actually modify this handout slightly from what's in the video, just to try to help accommodate for any changes. So maybe look for that on Monday if I've updated it, if I've had a chance to update it. And other than that, good luck.